Okay, class, welcome to the 11th tutorial of the course Symmetry, Stereochemistry and Applications, which is conducted by NPTEL, whose course instructor is Professor Anshuman Roy Chaudhary from ISER Mohali. I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay. In today's lecture, we are going to solve various questions on the topics, which is going to include last week's NPTEL topic taught in video lectures, which focused on various name reactions and their mechanism. Okay, so let us start with the first question. Here, this hydroxy substrate is given, diol substrate is given, and it is treated with acid in the reaction condition, and we get the cyclobutanone as the final product. At the very first glance, you may find it difficult to recognize the reaction looking at the complex starting material, but this reaction is following nothing but pinacolone rearrangement reaction. So let us look at the pinacolone rearrangement reaction mechanism, how it proceeds. Okay, so at first we always have the diol substrate in presence of acid in the medium. One of the two hydroxy groups get protonated as shown here. Okay, so this hydroxy group is going to extract a proton from the acid given to form this oxonium as an intermediate. Then this oxonium is going to undergo carbon oxygen bond breakage because this oxonium will readily lose a water molecule. So loss of water molecule happens and we get a carbocation in this second step. So after this carbocation forms, the stage is set for the key rearrangement step. Okay. So let us look at the subsequent step where the rearrangement finally takes place. So this carbocation is ready to undergo now alkyl shift as shown here. Since the adjacent carbon atom is having two methyl groups attached, one of the two methyl groups is going to migrate to the carbocation center, and we are going to get a new carbocation which is going to be stabilized by electron lone pair donation from the hydroxy attached to this carbon atom. Okay, the driving force of this rearrangement key step is to get a more stable carbocation in the subsequent step. Okay, this is why at first this carbon carbon bond breaks and this carbon carbon bond forms to give us a newer, more stable carbocation in its place. Now the oxygen of the second hydroxy group is going to donate its electron lone pairs towards the newly formed carbocation to give us the second oxonium intermediate. Okay, and the second oxonium intermediate now undergoes deprotonation to give us a ketone as the final product. Okay, so I hope all these four steps are clear to you. Now we will go back to our substrate and see how the reaction is taking place in this substrate given. So, at first, in presence of the acid in the reaction medium, this hydroxy group is going to get protonated to give us oxonium. Okay, and in the next step, loss of water molecule will take place and we will get a carbocation. So this is going to be the first carbocation which will form in the reaction. After this, the more stable carbocation will form by alkyl migration from the adjacent carbon. So this is the adjacent carbon to the carbocation and this alkyl chain will migrate. And here we get the second carbocation intermediate. After this step, the oxygen lone pair is going to donate electron pairs towards the carbocation and we will get the second oxonium in the reaction. Sorry. Okay, and in the last step, what will happen? It will be deprotonation. Okay, and the deprotonation is going to furnish the final ketone product. I hope it is clear to you now how the alkyl shift is happening and we are getting the cyclobutanone as the final product. So here, this is another example of pinacol-pinacolone rearrangement. Let us see how this mechanism happens. Okay, you may get first confused that the direct diol is not provided here. It is just an hydroxy epoxide given, but the basic mechanism which the reaction is going to follow will be the same. Okay, which we just now revised. So here in this case, what happens in presence of BF3 iterate Lewis acid, which is going to coordinate with the epoxide oxygen. Ring opening will take place to give you the first carbocation which forms in the reaction. So here you can place both the substituents as it is. I'm just showing what is happening with the epoxide ring. Okay. So this epoxide ring gets opened because of the binding with the BF3 iterate Lewis acid. And here we are going to have the carbocation. Now, as we have already seen that after the formation of the first carbocation, alkyl migration happens to give you a more stable carbocation because that carbocation center will be linked to the second hydroxy group, and the oxygen lone pair donation will stabilize the carbocation which is going to form newly. So in this case, the R group here is going to migrate to the carbocation center, and we are going to get an intermediate of this type. Then, after getting this second carbocation, The oxygen is going to donate its lone pairs to give us the oxonium ion. And that oxonium, after deprotonation, is going to give us the final keto product. In this case, beta hydroxyketone. Okay, so this oxonium is going to give us the final product after deprotonation step. So I hope pinacol-pinacolone rearrangement reaction mechanism is clear to you now. Let us move to the next further name reactions. So next we have this question from Hoffman rearrangement reaction. So we have this amide given, and the amide is treated with PIDA and potassium hydroxide base. PIDA is nothing but a hypervalent iodine reagent. We're going to see how it is going to participate in the reaction mechanism. And this amide is ultimately getting converted to this amine without affecting any other functionality present in the substrate. Okay, so this reaction is following Hoffman rearrangement reaction mechanism. Let us see how a typical Hoffman rearrangement reaction takes place, and then we are going to go into the detailed mechanism of this particular reaction in presence of PIDA. So, if an amide is treated under Hoffman rearrangement reaction conditions, the base is going to extract a proton from the amide to give us a negative charge centered on the nitrogen atom. Now, the negative charge is going to react with bromine in the reaction medium, and a bromide is going to be knocked out. And the product form is going to be this bromoamide. Now, another molecule of base is going to extract the second amide proton to give us this negative charge, which is going to be in conjugation with the carbonyl group. This will now undergo bromide elimination reaction to give us the reactive intermediate isocyanate which forms in the reaction. This isocyanate is now going to react with a water molecule. This water molecule is going to attack at this carbonyl. Okay, if we show, this water will attack here. The bonds are going to move like this, and we get this carbamic acid. Okay, and this carbamic acid now falls apart to give us a molecule of carbon dioxide along with primary amine. And this is how Hoffman rearrangement reaction converts an amide into an amine. Okay, so now if we go back to our question, you see that here bromine is not given in the reaction medium. So how PIDA is going to participate in the reaction in place of bromine, we will see now by going to the mechanism followed in this particular reaction. So this amide is given, right? Let us just denote the side chain as R. Okay, the base is present, which is potassium hydroxide, that is going to extract the proton from the amide to give us the negative charge, which can also form this imine as an equilibrium, and then this enolate can attack at the iodine center of the PIDA, and we get this N haloamide. This acetoxy group will be knocked out from PIDA, and N nitrogen atom of the enolate will be attached to this iodine, and this iodine will be attached to phenyl and an acetoxy group. Okay, one acetoxy will be knocked out, and this this whole group, which is going to now attach to the nitrogen atom, is denoted as X here. Okay, this behaves the same as any other nitrogen haloamide. Now this haloamide is going to react with another molecule of potassium hydroxide, and this is going to extract the second proton of the amide to give us this enolate. Further, as we have already seen, this enolate will now undergo rearrangement and elimination to give us isocyanate intermediate product. This isocyanate will take up a water molecule now to give us carbamate, carbamic acid, and this carbamic acid will now undergo CO2 elimination, as we have already seen, to give us a primary amine as the final product. Hence, the amide which is given in the question is going to undergo Hoffman rearrangement in presence of PIDA potassium hydroxide in water dioxane solvent system to give us the required primary amine. Let us now further go to the next question. So here we have benzoic acid given, and it is treated with thionyl chloride first, followed by sodium azide, and lastly it is heated in presence of methanol, and as the final product we are getting a carbamate. Okay, so this question is following Curtius rearrangement mechanism. Let us look at the typical reaction mechanism, how this reaction takes place. Okay, so what happens here, the benzoic acid which is given, this in presence of thionyl fluoride is going to form an acid chloride, which then undergoes reaction with sodium azide to give us this azide as the intermediate product. Now, as it has been shown here, the azide will then fall off and will give us a nitrogen molecule elimination as shown here. This will follow this pathway, and in presence of heating it will give us isocyanate intermediate. And lastly, since in the question it is heated with methanol, the isocyanate is going to react with a methanol molecule, to give us this carbamate as the final product. I hope now it is clear to you how we are getting this particular carbamate product. Next question is from another very similar reaction, which is Lawson rearrangement, where the carbamate is heated or in presence of acid, it falls apart into an isocyanate and an acid molecule. And the reaction mechanism involved in Lawson rearrangement goes as follows. The acid, the base, okay, so the base is indicated as A minus, and the base is going to extract a proton from the carbamate to give us a negative charge centered here. Then this negative charge will now push its electron pairs towards the carbonyl group, and the alkyl group and will hence migrate to the negatively charged nitrogen atom, leading to the breakage of nitrogen oxygen bond. Hence, this molecule, this intermediate, gets broken down into two parts, one of which is isocyanate and the other is acid. Hence, in this reaction, these are the two products which we are going to get. Now, in the next question, we have cyclohexanone given, and cyclohexanone is treated with hydroxylamine for followed by heating in presence of either acetone or acid solution, and we get a cyclic amide with an increased member of the ring as the final product. Okay, let us see how this reaction is going to take place, starting from a ketone to an amide, a cyclic amide. So this reaction is actually following the mechanism of Beckmann rearrangement. So let us see what happens in Beckmann rearrangement. At first, the ketone is going to react with the hydroxylamine as shown here. The nitrogen atom is going to attack at the carbonyl, which will lead to the formation of this oxyanion, which will then take up a proton from the water molecule present in the system to give us this hydroxylamine as the intermediate proton. This will now undergo elimination as shown here. The nitrogen is going to push its electron pair towards this nitrogen carbon bond, and this hydroxyl group will be eliminated. Then in the next step, deprotonation will happen from the nitrogen center. The base present in the reaction medium is going to extract this proton from this positively charged nitrogen center. And after deprotonation, we get this oxime as the reaction intermediate product. In the next step, the oxime is going to react with acid. Okay, because in the second step, if you remember, acid was added along with heating. So this oxime is going to take up a proton to give us this oxonium intermediate. And this is the redetermining step because the rearrangement reaction is going to happen after formation of this oxonium ion. Alkyl chain, which is trans to the oxonium, is going to shift to the nitrogen atom. And because of this alkyl chain migration, the water molecule from the oxonium is going to be knocked out. And we get this carbocation now. This carbocation in the subsequent step is going to react with another water molecule to give us the second oxonium ion. Now the second oxonium is going to undergo deprotonation reaction to give us this enol product. The enol will now undergo tautomerization and deprotonation to give us the final amide product in the reaction. So in total, six steps are involved in the Beckmann rearrangement reaction. And here are the list of bonds formed and bonds broken during the course of the reaction mechanism. Okay, you do not have to memorize anything. You just have to look at the reaction conditions, and as you start with the reaction of the ketone and the hydroxylamine, automatically you will be move forward towards the end product amide. Okay, hence by following the Beckmann rearrangement, we are getting this seven membered cyclic amine starting from the cyclohexanone reactant. Okay, I hope this is clear to you. Now we have another rearrangement reaction given here. We have 2-chlorocyclohexanone and an alkoxide, which is finally converting the six-membered ring to a five-membered ester. Okay, if you recall the name reactions taught in the video lectures, you must find it familiar because this reaction is following the Favorsky reaction mechanism. Let us see how Favorsky reaction mechanism takes place. So we have a halo ketone, alpha haloketone, and alkoxide in the reaction medium. So what happens? The alpha haloketone at first reacts with the alkoxide as shown here. The alkoxide is going to take up a proton from this alpha position, which will then convert the substrate into an enol, and this enol undergoes a three-membered ring formation by dehallucination. Okay, since this double bond is attacking at this alpha position where the halo group is attached, we get this fused cyclic intermediate in the reaction. Further, another molecule of alkoxide is going to attack at the carbonyl carbon and will lead to the breakage of the highly strained three-membered ring of the fused intermediate product. Okay, it attacks here and we get ring opening of this three-membered ring. And after the ring opening, the carbocation which is going to form, the anion which is going to form, is going to take up a proton from the solvent to give us this five-membered ester. Okay, I hope it is clear to you how starting from an alpha haloketone, we are getting a five-membered ester as the final reaction, final product. This is how the alpha halocyclohexanone, alpha chlorocyclohexanone reacts with a molecule of alkoxide to give us this 5-membered ring containing ester as the final product. Let us now move to the next question, where we have this aldehyde given along with sodium azide in presence of striplic acid in acetonitrile solvent. And the product, as you can see, the aldehyde functionality is replaced by a cyano group. So let us see how this reaction mechanism is taking place. Okay. So, starting from an acid, this reaction mechanism is actually following Smith reaction condition. So let us look at the general Smith reaction mechanism first, and then we will go to the particular mechanism which the reaction given here is following. Okay, because the typical Smith reaction starts from an acid, and the reaction which is given here is starting from an aldehyde. So the acid at first get protonated in presence of the acid medium present, and you can skip these steps and you can simply write the azide reaction with acid to give us RCON3 intermediate product. And this formation we have already seen in the Curtius reaction mechanism, Curtius rearrangement reaction mechanism. And the RCON3 is now going to undergo a nitrogen molecule elimination to give us the isocyanate intermediate. And the isocyanate intermediate, as we have already seen, is going to react with water molecule to give us carbamate first, and then that carbamate eliminates carbon dioxide to give us primate amine. In this particular reaction which is given, where aldehyde is converting to a cyanide, the sodium azide reacts with acid to give us HN3, and that HN3 reacts with the aldehyde where the azide attacks at the carbonyl carbon. Subsequently, water molecule gets eliminated from the hydroxyazide and we get this azide intermediate which immediately undergoes nitrogen molecule elimination and deprotonation to give us an aryl cyanide as the final product. This is how this aldehyde is getting converted into the aryl cyanide. Let us now move to the next question where benzylic, this compound is called benzyl and in presence of potassium hydroxide in the reaction medium, benzyl is getting converted to benzylic acid. Let us see how the mechanism is going to take place. At first, the hydroxide is going to attack at one of the carbonyl centers to give us the oxyanion, which then undergoes alkyl migration from the alpha position to the beta carbonyl center, and this migration is going to give us the second oxyanion. And this second oxyanion is now going to take up a proton from the system to give us the benzylic acid as the final product, and this rearrangement reaction is called benzyl benzylic acid rearrangement reaction. Okay, I hope this reaction mechanism is clear to you. Next we have Fry's rearrangement or Freeze rearrangement, where we have phenol and we have prepared the ester from the reaction of anhydride with phenol, and upon treatment with aluminum chloride we get migration of it is actually written wrong. This O is not required here. The COCH3 will be attached. Okay, directly COCH3 is going to be attached. By mistake, an oxygen is mentioned extra here. So the COCH3 group migrates from the ortho ester group to ortho and para positions. So let us look at the phase rearrangement reaction mechanism. What happens? The ester at first reacts with the aluminum chloride, which is given to give us a complex as shown here. This complex then dissociates to form acylium ion as shown here. Okay, and this acylium ion can be attacked by the aromatic ring, which is preferred from the ortho position or the para position. This is why the COR group is attached in the ring in the subsequent product which is going to be formed. So this particular reaction is called freeze rearrangement. A very similar reaction mechanism is followed in Claisen rearrangement reaction. Okay, so this reaction which is given here is following Claisen rearrangement. Let us look at the typical reaction mechanism of Claisen rearrangement, after which we are going to look at the exact mechanism which is going to be followed by this particular reaction. So this 3,3 sigma tropic rearrangement mechanism is followed in Claisen rearrangement. This allyl group is going to attack at the ortho position of the aryl group, and the carbon-carbon double bond in turn will get converted to a carbon oxygen double bond as shown here. This then undergo tautomerization to give a more stable compound which is ortho-substituted phenol. So in the reaction given, what happens? The starting material undergoes a Claisen rearrangement, 3,3 sigma tropic rearrangement as shown here. This double bond will first attack at the neighboring ring carbon-carbon double bond, which will then undergo rearrangement to give us a carbon-oxygen double bond at this position. And this carbon-oxygen bond is going to break. This is how we get this Claisen rearrangement final product as the product in this given reaction. Thus, we have solved today various questions from the topic rearrangement reaction. Let us quickly revise the questions which we have covered today in this session. Okay, we started our session with pinacolone rearrangement reaction, where we converted this diol into the cyclobutanone given here in presence of acid solution. And we went through the reaction mechanism which is involved in pinacolone rearrangement, and hence we figured out that the oxonium undergoes water molecule elimination followed by alkyl migration to give cyclobutanone as the final product given. Another question we solved from the topic pinacolone rearrangement, and here we saw that epoxide ring opening took place first, followed by alkyl chain migration to give us more stable carbocation, and hence to give us the beta hydroxyketone as the final product. After the pinacolone rearrangement, we went through the mechanism of Hofmann rearrangement, where we saw how isocyanate intermediate is formed, which reacts with water molecule to give carbamic acid. And in our reaction, PIDA was replaced in place of bromine, and we got N-haloamide, which followed the same mechanism as typical Hofmann rearrangement. After that, we went through the mechanism of Curtius rearrangement reaction and a very similar reaction, which is Lawson rearrangement reaction. And then we saw how a very long reaction mechanism is followed in case of Beckmann rearrangement, and these were the bonds formed and bonds broken throughout the course of the reaction. After Beckmann rearrangement, we also discussed Favorsky rearrangement, where the alpha haloketone was getting converted to an ester. Along with Favorsky, we also discussed Schmidt reaction mechanism and benzyl benzylic acid reaction mechanism. We had also discussed Fries rearrangement and a very similar Claisen rearrangement, where 3,3 sigma tropic rearrangement reaction was involved as the mechanism. So thank you very much for joining for today's live session. We will be meeting tomorrow again for an extra session where we are going to summarize the topics we have covered till now. Okay, along with that, in the last tutorial, which is going to take place next Friday, we are going to discuss the last week's video lectures topics, and we are going to solve a few questions related to the last week's topics. Okay, so looking forward to meet you tomorrow again for the extra live session. Thank you very much for joining today.